Hello, and welcome to the Xi Engineering Consultants tutorial on how to connect and use the COMSOL applications that we create for our clients. This service allows our clients to interact with the complex multiphysics models that we have created, allowing them to change model parameters such as material properties, component dimensions, or even adding in additional supports for a structure. To connect to our COMSOL server, all our clients need is internet access in a web browser, such as Google Chrome or Internet Explorer. Xi will issue a username and password for our clients to connect to our online server. Once connected, the user can see the application library. This is where the user can see all of the apps that they have permission to access. Our client, App Tutorial, is a guest user and only has access to the applications that have been assigned to the user. We have some acoustic applications looking at the dynamics and noise propagation from speakers, wind turbines, and tidal turbines. We also have some structural analysis applications, one of which we are going to look at today. The floor frequency response analysis application looks at the dynamic response of a floor due to excitation from rotating machinery. To launch the application, simply click the Launch in Browser button. I already have one open, so I'll bring it up just now. Once the app is open, we can see the graphical user interface created by Xi Engineering Consultants. So the aim of this model is to design a room to support an array of rotating machines. According to the client's design specification, the first resonance of the room must be greater than 8 Hz, and there should be no frequency matching issues whilst the machines are in operation. An example of destructive frequency matching is when the operational frequency of a machine matches a structural resonance. This can cause high stress cycles and ultimately lead to structural failure. Over on the left hand side here, we have the Inputs tab. This is where we change model parameters such as the room dimensions, number and size of supporting beams, and even the weight of the machines to be mounted onto the floor. Down at the bottom we have the Graphics tabs. This is where we can see the model geometry. This view is a 3D structural mechanics model, which gives us a good representation of the model we are building. However, it can be quite computationally demanding to run analysis on this type of component, so we have also parameterized shell geometry, where we have assigned the same thicknesses and boundary conditions as the 3D model. All analysis will be run on the shell geometry. Up at the top we have the table of results. This is where we can compute the maximum displacement and maximum acceleration on the floor as a result of the operating machines. Over here we have the inputs for the modal analysis and frequency response analysis that we will be performing on the model geometry. So let's begin by changing some of the room dimensions. Let's change the room width to be 15 meters by 10 meters and give us a thickness of 200 mm. And we can see our new design by clicking on the Plot Geometry button. And now we can see that our floor has updated. But we're probably going to need some extra supporting beams for our floor. Okay, let's say 3 small supporting beams instead of 2. These beam dimensions have been taken from the British Universal Beams and Columns tables, and the main beam has had holes designed into the web to accommodate building services such as air vents and cable management. Now let's say we're going to have 6 machines on our floor, but we only want them on one half of the room because we're going to have other processes going on at the other side. Let's start off by making our pads a bit thicker, let's say 100 mm, and our machines are going to be a bit smaller, so let's make the pads 2 meters by 2 meters. Now we can plot that here and see what it looks like. Okay, so we're happy with the design. Now let's look at changing the array. Let's say we want 6 machines, so let's plot them 3 by 2. And now let's see what that looks like. Okay, so it appears we have overshot our geometry a little bit. So let's make the x distance down to 1.5 meters and the y distance down to 1 meter. Now that looks much better. Now let's look at our machine parameters. Let's assume that these machines are going to have quite a lot of force coming off them. So let's change the force in the x direction to 1 kN per meter squared and the y direction to 500 newtons per meter squared. It should be noted that the x and y forces are 180 degrees out of phase from each other. Okay, our room looks ready now. So I'm now interested in what the lowest resonances are going to be in my floor. Before we compute the modal analysis, however, we first have to find the right mesh for our model geometry. By clicking on the drop down menu over here, we can select what size of mesh we would like to build. A coarser mesh has much less accuracy than a fine mesh, however computation time is also decreased. If we select a very coarse mesh and then click on plot mesh, we can see that the mesh is very sparse and we've actually lost all definition around the holes of the main supporting beam. We don't want to lose definition in our beams because we are concerned with the stress concentration around the hole cutouts. So let's try selecting a normal mesh. Again, that we can see there is loss of definition on the main beams and the holes are still appearing as a diamond geometry. Okay, so let's go for an extra fine mesh. Now we can see the holes are almost complete circles and there is good mesh density throughout the model. We are now confident that the mesh should return accurate results and we are now ready to compute our modal analysis. So look over here, we can choose how many eigenfrequencies we would like to find. Just to get an idea of the first few bending modes, we will keep it as 6 eigenfrequencies for the first analysis. To compute the eigenfrequency study, simply click on the Modal Analysis button here. Now this shouldn't take long to compute. I'll say now that we haven't built in the option to change any material properties in this application or to design a component specific mesh. It is just a simple model that I've put together for the sake of this tutorial. Now I'll cut the video whilst the computation is running and I'll start the video once it has completed. Okay, so now the modal analysis is completed. If we go to the Modal Analysis tab, we can see a plot of the first 6 mode shapes of the factory floor. We can see from the results that we still have really low frequency resonances in our floor, which we're going to try and remove. The floor seems really flexible, so I think we should start adding in a few more supporting beams. Let's try with 5 main support beams and 8 smaller beams and running the analysis again. When you click the Compute button, the app automatically plots the new geometry and builds a mesh to the same parameters as used previously. Looking at the results of the analysis, we can see that the first mode shape occurs just above 8 Hz, which is much better than the previous design. Now we need to put in the frequency that machines are going to be operating at. We know the machines operate around 45 Hz, so let's do a frequency analysis between 43 and 47 Hz at 0.1 Hz steps. This will give us a good idea of the frequency response of the floor whilst the machines are in operation. Just click the frequency response button to begin the analysis, and I'll cut the video here whilst the analysis runs. Now the frequency response analysis has finished. So if we go to the frequency response tab and look at the mode shapes, we can see that most of these frequencies have some areas of excitation. So let's have a look at the results table to get a better idea of what the numbers actually are. If we go up to the displacement table, we can record our results. We'll need to click on the Reset Table button as there's currently no data in the table to view. Clicking Update Table will generate a new column in the table to compare results from different tests. If we want, we can export the results from the table and save them in a spreadsheet using these buttons here. To get a better understanding of how the numbers work, we can plot them in a graph, and we can see that down in the Graphics tab. If we have multiple sets of results, we can click on the Show Legends button to see the column headers that the results are coming from. Looking at the graph, we can see there is really large displacement around 44.7 Hz. The maximum displacement reaches 28 mm, which suggests there is destructive frequency matching between a resonance in the isolated room and the operating frequency of the machines. If we want to export the graph, we can save it using the Snapshot button here. Now let's have a look at the mode shape. There are clearly multiple areas of high excitation at this frequency, suggesting we will need to reconsider the supporting structure for the floor. Let's have a look at the von Mises stresses of the factory floor. We can see the stresses for the 44.7 Hz frequency. It's quite clear that there are high stress concentrations in the supporting beams, so possibly adding in some additional beams would help relieve the stress on the beam and dampen the floor's response to the operating machines. It looks like we might need to redesign our floor if we are going to support the machines during operation. If we are happy with the work we've done, we can save an updated version of the app onto the server using the Save App button. If we don't want to save, we can simply click the Restore Defaults button to change all the model parameters back to their default value, and we can see that by plotting the default values again. I hope you've enjoyed our tutorial. We can customize the computations and outputs from our applications to fit our clients' needs. If you have any questions, or if you would like to use our modeling service, please click on our website link below. Thank you.